Well, a warm welcome to everybody here. Thank you for being here. We're going to have a very, very chill experience, but you should still get yourself prepared. With a notebook, grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a problem from the 2002 AP Calculus BC exam. Now, even though this problem is from the BC exam, AB students, do not be scared away. You can totally answer this question. It's possible that this question was also on the AP exam, given that the BC exam contains about 2/3 to 3/4 of the exact same question. Alright, this one is about differential equations. So I want you to give yourself about 12 minutes. Go ahead and work on this on your own. And then when you're ready, you can come back and see how it's done here. Now, we only have two parts represented here, so that's kind of a clue that there's going to be quite a bit of work asked from each part. In fact, part B, I guess, can have up to 5 or 6 points out of the 9 for the question. So let's take a look at this. We have a differential equation, dy dx, which of course tells us the slope of the tangent line at some x and y location on a curve. Let's get started with part A. Let y equals f of x be a particular solution to the given differential equation, such that the line y equals -2 is tangent to the graph of f. Okay, so what does that mean? That means that a horizontal line is tangent to the graph at some point. We know what the y value is, somewhere on that line. We don't know exactly where the curve touches it. It could be going like that or something, or it could be coming from above. Who knows? Find the x-coordinate of the point of tangency and determine whether f has a local max, min, or neither. Of course, you need to justify your answer to determine that. You don't just guess. What do we know about a function that is tangent to a horizontal line? A function which has a horizontal tangent has a slope of 0 at that point. So we're basically going to set this equal to 0. And of course, a fraction is equal to 0 when its numerator is equal to 0, and its denominator must not also be equal to 0. So if this is true, then we know 3 minus x must also be 0, which of course means x equals 3. So here's the point of tangency, in a sense, 3 comma -2. That's the first part of this answer. The second part is to determine whether there's a local maximum, minimum, or neither there. So we know where it's located at, but we still don't know if this represents a high point, a low point, or maybe neither. If the function goes like this, then it's neither, or if the function goes like this, in any way, it's neither. But if the function is sort of going like this, it's a maximum, and if it's sort of going like this, it's a minimum. So how do we figure that out without the function equation at our disposal? Well, we have to take a look at the concavity. Because if the concavity is positive, then this would represent a minimum. If the concavity is negative, this would represent a maximum. And if the concavity is 0, this would represent neither a maximum nor a minimum. So let's find the second derivative. Yes, the second derivative is going to require taking a derivative of the first derivative, of course. So we're going to take a derivative of 3 minus x over y, which is going to require the quotient rule. I almost said the product rule and the chain rule, which both of those are incorrect. We're going to use the quotient rule. Good old low-d high, y times the derivative of the top, minus high, that's the top function, d low, that's the derivative of the bottom. Can't forget to square down below. Now at this particular point, where x equals to 3, this is pretty easy to evaluate. So we're going to say like at the point 3 comma negative 2, this is simply going to be equal to negative 2 times negative 1 minus, both of these terms go to 0. Both 3 minus x and also y prime goes to 0 at that point. It's the point of tangency, so we discussed that dy dx is 0 there at a horizontal tangent. Over the y squared, which is negative 2 squared. So careful, because there are lots of negatives here. We get 2 over 4, 1/2, which is greater than 0, which means f of x is concave up at that point. So f of x has a local minimum, or if you want to call it a relative minimum, at x equals 3. Bam, we determined that it has a relative or local minimum. And that's the justification. We used the second derivative test. We could say, like, if you really want to put that, you could. By second derivative test. Sorry for the sloppy writing there. I'm just trying not to waste all your time writing a couple words. Okay, let's move on to part B. It was a pretty easy part A. You probably get about 3 points, maybe 4, most likely 3. Part B says let y equals g of x be the particular solution to that given differential from negative 2 to 8. Okay, and let y equals g of x be the particular solution with this initial condition. So they gave us an initial condition. We already have an initial condition. That was 3 comma negative 2. And now we have another initial condition. That kind of hints that we're going to have some sort of exponential function. So I'm guessing we're going to have an exponential function. But let's separate this properly. Let's find, that's the goal anyways, let's find the function y equals g of x. First we'll have to take this differential equation and separate its variables. Multiply the y to get all the y stuff over there. Multiply the dx to get all the x stuff over here. And now we're ready to integrate both sides. This gives us 1/2 y squared. So maybe we don't have an exponential function. The differential equation would look a little bit different. This is going to be 3x minus 1/2 x squared. It's looking more like a square root function, actually. Okay, so let's use the initial condition here. G of 6 equals negative 4. We could solve or isolate the y now, but we don't have to. Maybe let's multiply everything by 2, though. That could help things. once you have an equation established, you have a little bit of freedom of what you can do with that equation. This is still just going to become a plus c. Not really a big deal there. And then we're going to take a square root, but first let's use the initial condition to find c. G of 6 equals negative 4. So the y value is negative 4 when the x value is equal to 6. Well, that works out kind of nicely, doesn't it, family? Because 36 minus 36 is simply 0. And so our c value here is 16. Now, be careful, that's the c value that goes with this equation, not the c value that goes with this equation. It's sort of like a different c. And that means we have this equation y squared equals 6x minus x squared plus 16. But we want to get the y by itself. So whenever you're taking a square root to solve an equation, you always want to consider the plus or minus case. So which one is it? If we're saying that this is a function, it can only be one of them. Because of course one square root is going to go something like that, and the other square root is going to go something like that. We can't have them both represented, otherwise this is no longer a function. Well, remember, our initial condition says that we have the point 6 comma negative 4. The square root is only going to give you a positive number, so this has to be the negative square root. Right, does that make sense? Like if I plugged in 6, I would have, again, square root of 36 minus 36 plus 16. Well, that's just the square root of 16, which is 4, but that's not the y value. The y value is negative 4. So hopefully that convinces you that we need the negative square root. There we are. And this gives us the original function. Now, I got to imagine that's only worth like 5 points, because the integration was not difficult at all. There was this small little situation where we had to worry about the initial condition leading us to an equation which considers positive or negative, but the initial condition really solidifies that it's the negative case. Other than that, not too much else used. We did use this calculus technique of the second derivative test to determine maximums or minimums by analyzing the concavity of the curve at a point. But other than that, relatively easy to deal with. So if you were in AB, I hope you gave that a shot as well. Very doable, very approachable from all of you. And that's enough blab out of me. See you guys next time in the void.